Hello, this is Dr. Lori. Welcome to the second part of our discussion on real-world graphs. And what I'd like to point out is that often when we are creating graphs, we think of it as an isolated activity, but really it is part of the overall question that we're asking. So here we have our research process. And in the just very broad sense, maybe we're doing this information for the county health department. It doesn't have to be something that's going to be a published peer-reviewed research article. The first piece of that is to ask a good question. And this asking of a question is tied inexplicably to every other part of the study, especially the graphs and the other results that we come up with. After we design the study, we collect the data and then analyze it. And then once we've analyzed it, we want to interpret it, share it, and this often then leads back to more questions. It's this analyzing part. This is where we are converting the data into information that these stakeholders can use. So in this sense, we do descriptive statistics, we do inferential statistics, and this descriptive statistics is both the pictures or the graphs and the numbers, which sometimes we call more generally descriptive statistics by themselves. So these pictures right here is what we're really working on. And so often we become so focused on that picture, the graph that we're making, that we forget about this larger process. We forget about that it's part of something that we're actually doing that is a longer sequence. And the reason that I bring that up is that it is very common, especially early on, that we create these wonderful graphs and we forget that it really needs to relate to the overall question that we were asking in our study. It needs to relate to that interpretation. The pictures ultimately come from the data and the study design. But these are the two areas that sometimes we end up seeing a mismatch. Do you remember in our practice article that we were looking at? In this particular report, we want to know what is the incidence of all of these different reportable diseases and who is it impacting. And so all of the graphs that we're making should really answer those questions. If we make a really fabulous graph that's completely unrelated, then we really haven't achieved our goal of answering that question. Or if we make a wonderful graph over here on the right-hand side, but it doesn't really also jive with the 2016 review information that we're summarizing in words, then we've sort of lost sight of keeping this as a cohesive whole. Not only should the graph itself be cohesive, but it should connect with all of the rest of the things that we're doing in this overall research process. And so just be sure that it seems so obvious, but this is one of the number one things that students miss early on, is they are so keyed in to making this graph that they forget how it needs to be connected to those other pieces of this research process. I want to highlight a few things that we've kind of talked about. Some is the terminology. We talked about morbidity and mortality and the difference between those. And part of learning any new profession is really understanding the lingo so that you can use words in a way that is accurate and concise and it means the same thing as what other people are using them. So morbidity is related to illness in individuals, and mortality is related to death. Incidence and prevalence are two related terms, and we'll find out more later about how they're related. But incidence is new cases. So if we're looking at that report for 2016, those are people who did not have these diseases before. And prevalence would be the existing cases, like at any given time, how many people are sick with the flu or how many people have HIV, those kinds of things. The other thing that's important to keep in mind with this particular study is the denominator data, because so many of the tables are reported in cases per, let's find one, incidents per 100,000. If you look at the y-axis on the tables that are showing the comparison between San Bernardino County and California in the United States and the Healthy People 2020 goal, this really has to be compared to what? Because if you looked at the United States overall, the absolute count would be much higher than California by itself. And even California by itself would be much larger than just the sub-county of San Bernardino County. So we have to have a denominator that gives us a common ground when we're comparing across different groups like that. So let's take a look at a few more of these. A lot of the different diseases have a similar look and feel. Shigellosis has a different top right graph. It does not look at race ethnicity. Instead, it looks across age groups. And so you can see that it's pretty evenly spread, it looks like, across those age groups. And then the second graph does look at your race ethnicity by ages. And here we see a little bit of seasonality where it's kind of going up during the year. One of the things that I do want to point out is that for a number of diseases we have pretty small counts, and that's wonderful. That's a huge success. We don't want them to be higher. But what that does mean is that if we think about what could possibly go wrong, a lot of times one of the things that you have to keep in mind is this problem with small numbers. And that is that if we're looking at a graph like this bottom right graph, when you look at, say, April for 2016 compared to March and May, the difference is goes from 1 up to 7. That's 700 times 700% or 7 times greater. But that would just be like a family, maybe an extended family or several people having more disease at that particular time. If the left-hand side were hundreds of cases, 100, 200, 300, that would be a pretty impressive difference. But since it's just individual cases, then just a few can make it really swing one way or another, up or down, quite significantly. So that problem with small numbers is a good problem, and it can also make the numbers be quite unstable from month to month or year to year. So here you can see San Bernardino is nicely situated, lower than California and the US overall. And then here we have HIV/AIDS. You can see what age groups we tend to have more HIV and AIDS. You can also see that for females, except for, and I see a little bit of an error on the x-axis here. It looks like those lower age groups, the numbers less than 1, 1 to 4, 5 to 9, 10 to 14, 15 to 19, and 20 to 24 have kind of gotten eliminated by accident. But you can see in that 20 to 24 age group, that's the primary age that females are really at higher risk for HIV/AIDS, and for the other age groups it's quite low. But for men, and so this really helps us remember um, the who, what, when, where kind of idea, the person, place, and time. We can think about things in terms of a variety of dimensions. And so this really helps us understand who our target would be if we're trying to create some kind of an intervention or a prevention. So here we have by race, ethnicity, white, black, Hispanic, and also the percentages of total. So now here we get a different kind of a graph where it's a stacked bar graph. The largest piece is MSM, or men having sex with men, injection drug use. There's a combination bar that's a little darker than that. There's heterosexual, other, and perinatal is really disappearing. 2014, 15, and 16 for San Bernardino, that's gotten squeezed out, but unknown has gotten larger. And so you can really kind of see a trend. Here's an excellent example of use of color where it's shading the different shades so that you can really tell the size of the width of the graph, but then also making sure that there's enough of a distinction between the the colors to be sure you can see that perinatal in between the other and heterosexual and unknown, and how it's kind of disappearing. So think about that use of color. And then I think we have a graph coming up here that has a gap that I wanted to show you. And here's something that we've kind of had a good understanding of for quite a long time. Just the age distribution of certain things. Syphilis being a sexually transmitted disease. You can see the ages and where that really starts to kick in, the difference between males and females, and a striking difference also between the different race ethnicities, white, Hispanic, and black. White, Hispanic, and black is often the three main race ethnicities, but every once in a while you'll see a table that pulls in another group that's at high risk. So pay attention to that when other race ethnicities are included. You can see a striking seasonality for pertussis. And in this case, you can notice the age groups are quite young. So there are just some real important differences between the different diseases. Here's respiratory syncytial virus, and it's the young and the old, much less common in the middle age groups, and a definite seasonal pattern that we see with RSV. One of the things that I like to pay attention to, and this could be something that's important for any disease, but the fact that on here we have tuberculosis, where we look and see where the region of origin is for San Bernardino County specifically. So people coming from different places, or just the fact that they acquired it here in the United States. And again, the use of color. So one of the things that I wanted to talk about back when we were looking at HIV is that over time the diagnostic criteria, or the ICD-9 or 10, what's used to define a case might actually change from one year to the next. And so what you can see from that is sometimes a spike of new incident cases, or you can see a drop at that point. And so that's one of the things that's important to think about is how did we come up with these cases? Here's coccidiomycosis, and there was a gap in the United States in 2010. And so we don't automatically just draw a line, kind of make sure that we don't want to convey information that's incorrect. We actually don't know. We don't know what that number would be. And so we can, going back to that previous thought, we can have a change in the way that the diagnosis is happening, the testing. So imagine, if you will, that you have a population that might have an underlying disease, hepatitis, or a variety of different kinds of things could fall into this category. But all of a sudden, maybe you have a training session for physicians, or a new type of test comes out that's more accurate or more precise. And so all of a sudden, you might see an increase in cases, and you might be thinking, hey, we're putting all this money towards this particular disease. Why is it going up? And it might just be that the diagnostic criteria, or the way that we're testing, or the training for healthcare professionals has changed. And so kind of keep that in mind as you're going through and you're seeing these rise and fall. Is it real? Or could it be that we're just changing the way that we're aware of that disease, or that we're testing for that disease, or the diagnostic criteria for that disease? I'm going to skip all the way to the end of this report. Oh, that was actually an interesting one. This has to do with rabies, and so the distribution. So instead of having other kinds of graphs, in this case, we have a map. And this is so amazing and appropriate. This totally shows how GIS is really important in terms of some kinds of describing the person, place, and time. So, and then we have California, rabies for California, actual rabid bats, or bats that were tested for rabies by the different counties, and the darker ones, we had more bats tested, and the lighter ones, the ones that are white, didn't have any bats tested. Okay, so I'm going to scroll all the way to the end, and we have all these appendices, but the very last page I think is a really important one to think about. So Appendix E, data sources. I want you to remember we designed studies and collected data in order to be able to use them for this report. And look at how many different places this came from. For all of the diseases except for HIV, which has different data sources, so all these top ones, the incidence data came from San Bernardino County communicable disease records. So think about all of what would need to go into collecting the data for that. And compiling it. Basically, data comes in and it's compiled on a weekly basis so that it can be monitored, sometimes more frequently if we have a disease that's really unusual. The California data came from a variety of different places depending on what disease it is. And then for the United States, we also have reportable diseases that go all the way to the CDC, and for different types of disease. For AIDS and HIV, it's a separate process, and that's because of the sensitivity around the stigma that comes with HIV. Remember how I said that we need to know what our denominator data is? Here where it says population data, that for California comes from the Department of Finance. And so we have detailed census data, and then we have projections, and for the United States, the Census Bureau does the national population projections, and so we need to come up with how big we think the whole entire group is in order to know what the incidence per 100,000 is for that particular group. The Healthy People 2020 objectives came from the healthypeople.gov website, And there are also the general disease facts and data that were listed on each of those pages. So think of all of the different places that information comes from, so that if I go back to here, number 7 says synthesize information from multiple data systems or other sources. That kind of a report really has to pull information from so many different places. All of those graphs need to be made so that they are conveying so many different kinds of pieces of information so that these stakeholders can make decisions. So that concludes this talk on graphs and all of the different kinds of things that go into this whole research process.